Let us write the integrated rate law for a zero order reaction. So let us consider a zero order reaction are giving products. Since the reaction that we have considered is zero order, I can write the differential rate law as minus dr divided by dt is equal to K into concentration of R naught raised to 0. So this is equal to K into 1. So therefore I can write the differential rate law is minus dr divided by dt is equal to K. Rearranging this equation, I can write minus dr is equal to K into dt. Changing this minus side towards the right hand side, I can write dr is equal to minus K into dt. Integrating on both sides, I can write integration of dr is equal to minus K is a constant, integration of dt. Integration of dr gives us r, which is equal to minus K. Integration of dt is t plus c. So the c is constant of integration. Now let us find the value of C. After integrating the differential rate law, we have arrived at the expression concentration of R is equal to minus Kt plus C. Let us denote this equation as 1. Here C is constant of integration. Now let us find the value of C considering the initial time t is equal to 0. So when time was 0, during the beginning of reaction, concentration of reaction was equal to the initial concentration of the reaction R naught. Let us substitute this in equation 1. So now at time t is equal to 0, concentration of R is R naught, which is equal to minus K, time is 0 plus C. So therefore we can write C is equal to R naught. Let me denote this as equation 2. Now I'll substitute equation 2 in 1. That is, I am substituting value of constant of integration into equation 1. So I can write concentration of R is equal to minus Kt plus C is R naught. Rearranging this expression, I can write Kt is equal to R naught minus R, and therefore rate constant K is equal to R naught minus R divided by T. So this is the expression for rate constant of a zero order reaction, and the integrated rate law for zero order reaction is R is equal to minus Kt plus R naught. Either any of the formats you can write it. This gives the integrated rate law for a zero order reaction. If I consider the equation concentration of R is equal to minus Kt plus concentration R naught. Let me write this as equation 3. If I consider equation 3, that is concentration of R is equal to minus Kt plus initial concentration of reactant. This is of the form y is equal to mx plus c, which is a straight line. So when I plot a graph of concentration of reactant R versus time, I will get a straight line graph. So this is the graph that you will get when you plot concentration of reactant versus time. So here we see that the intercept is the initial concentration of the reactant R naught, and slope of the graph will give us rate constant. Okay, so rate constant is equal to minus slope. So by calculating the slope, we can find the rate constant for a zero order reaction. Example for zero order reaction is decomposition of gaseous ammonia on the hot platinum surface at high pressure. This is the corresponding chemical reaction. It decomposes to give hydrogen and nitrogen gas. For this reaction, rate law is written as rate is equal to K into concentration of NH3 raised to 0, and therefore we can write rate is equal to rate constant. Now let us derive the integrated rate law for a first order reaction. So let us consider a first order reaction are giving products. We know that rate of a first order reaction is directly proportional to the first power of concentration of reactants. So therefore I can write rate law, rate is equal to K into concentration of R raised to 1. So the differential rate law is minus dr divided by dt is equal to K into concentration of R. Rearranging this equation, we can write dr divided by concentration of R is equal to minus K into dt. Integrating this expression on both sides, I can write integration of dr divided by concentration of R, which is equal to minus K is a constant, integration of dt. So we know that integration of 1 by x into dx is ln x. So here integration of 1 by r into dr is ln r, which is equal to minus k. Integration of dt is t. So it is k into t plus integration constant c. So right, c is constant of integration. I'll denote this equation which is obtained after integration as equation 1. Now let's find the value of integration constant and substitute it. And time is 0. We have concentration of reactant R is equal to R naught. So that is the initial concentration of the reactant. So let me denote this equation which is obtained after integration as 1. In that expression, when time t is 0, concentration of reactant is R naught. So ln R naught is equal to minus K time t is 0 plus C. So therefore, we get constant of integration C is equal to ln R naught. Now let's substitute C in equation 1, and therefore I can write ln R is equal to minus Kt plus ln concentration of R naught. I'll write this equation as 2. Now if we observe this equation 2, this is of the form y is equal to mx plus c, which is the expression for a straight line. Now let us plot the graph of ln concentration R versus time t. We will be getting a straight line. In this graph, intercept will give us ln R naught and the value of slope will give us rate constant K. So from this slope, negative of this slope will give us rate constant. If I rearrange this equation 2, I can calculate the value of rate constant. So we shall rearrange it. I can write Kt is equal to minus ln R plus ln concentration R naught. So this is ln R naught minus ln r, which is equal to kt. From the laws of logarithms, if we have ln m minus ln n, we can write it as ln m by n. Similarly, here I can write this is ln r naught divided by r, which is equal to kt. And therefore, I can write k is equal to 1 by t ln r naught divided by r. If I need to write this natural log in terms of logarithm to the base 10, I have to multiply it with 2.303. So the value of k is equal to 2.303 divided by t log of r naught divided by r. So it's using either of these two expressions, you can find out the value of rate constant mathematically. So from equation 2, at time t1, I can write ln concentration R1 is equal to minus k T1 plus ln concentration R0. And similarly at time T2, I can write ln concentration R2, because at a time 2 concentration of reactant will be R2, that's equal to minus k T2 plus ln R0. Let me denote these two equations as equation 3 and equation 4. Subtracting equation 4 from equation 3, I can write ln R1 minus ln R2 is equal to minus KT1 plus ln R0 minus of equation 4, it's minus KT2 plus ln R0 is equal to minus KT1 plus ln R0 minus of minus plus KT2 minus ln R0. So ln R0 terms gets cancelled with one another. On the left hand side, we have ln R1 minus ln R2. Using laws of logarithms, I can write this as ln R1 divided by R2. So now this is equal to k T2 minus k T1. So rate constant is same. So it's k is common, k into T2 minus T1, which is equal to ln R1 divided by R2. And from this I can write k is equal to 1 by T2 minus T1 ln R1 divided by R2. So using this expression, we can determine rate constant for a given reaction at two different time, T1 and T2, and the corresponding concentration is R1 and R2. So if we want to determine rate constant in terms of logarithm to the base 10, I have to multiply here with 2.303 divided by T2 minus T1 log of R1 divided by R2. So making use of any one of these expression, we can determine rate constant at two time T1 and T2 when corresponding concentration of reactants is provided to us. Again, considering equation 2, we can write this as ln R0 divided by R, which is equal to minus KT. Taking antilog on both sides of this equation, you can write this as R0 divided by R is equal to e to the power minus KT. And therefore, we can calculate initial concentration of the reactant R naught, that is equal to concentration of the reactant at the time interval T, that's R into e to the power minus KT. So this is how we can determine the initial concentration of the reactant involved in a reaction. We had written the expression for rate constant as K is equal to 2.303 divided by T log R naught divided by R. This can be rearranged and we can write it as log R naught divided by R, that's equal to K into T divided by 2.303. So here now if we plot a graph of log R naught divided by R versus time, we will get a straight line graph. Slope for this graph is equal to K divided by 2.303. So this, using this slope value, we can calculate rate constant. So that is equal to 2.303 into slope. Hydrogenation of ethene is an example for first order reaction. Chemical equation is C2H4 gas plus H2 gas. So we all know that hydrogenation is addition of hydrogen. So that alkene is getting converted into alkane. So ethane is the product that we are going to get. So if we write the rate equation, we observe that rate is equal to K into concentration of C2H4. Another example is decomposition of N2O5. Also the decomposition of N2O are first order reaction, and you should remember that the natural and artificial radioactive decay of unstable nuclei are always a first order reaction. So this is important to remember. Natural and artificial radioactive decay are first order reaction. For example, radioactive decay of 88 radium 226 to form helium and radon is a first order reaction. So the experimental rate equation here is observed to be rate is equal to rate constant into concentration of radium. Let us discuss how we can write integrated rate equation for a first order gaseous reaction. So for this purpose, let us consider a first order gaseous reaction. Where from gaseous reactant A, we will be getting gaseous products B and C. Now let us consider initial pressure of A as P1. So let P1 be initial pressure of A we are considering pressure here because for the gaseous reactants or products, its concentration is represented in terms of its partial pressure. So here P1 is the initial pressure of A, and let us consider PT as the total pressure. At time T. So this total pressure Pt at any time, if we consider, that will be the sum of pressures of reactant A and products B and C. So units will be in terms of units of pressure. Here PA, PB, PC are the partial pressures of A, B and C respectively. If I consider the reaction A giving products B and C, initially when time t is 0, we have the pressure of reactant, that's the initial pressure, P1 atmosphere. So no products will be formed initially, so it is their pressure is 0 atmosphere. Now at a time t, let us consider the decrease in pressure of reactant B, X atmosphere. So the pressure at the time interval t will be P minus X, because X atmosphere decrease is observed in the pressure of the reactant, because reactants are getting converted into product, and therefore pressure of products will be X atmosphere each. Now at time t, total pressure is Pt, so which is sum of the pressures of A, B and C. So that is P1 X plus X plus X, which is the pressures of A, B and C. So here minus X and plus X gets cancelled with one another. So I can write Pt is equal to P1 plus X. So rearranging this expression, I can write the decrease in the pressure of the reactant X is equal to Pt minus P1. Let me write this equation as 1 and the equation for X as 2. We know partial pressure of A, that we have represented as PA at time t is equal to P1 minus X. So here I will substitute X is Pt minus P1, which is equal to 2P1 minus Pt. So we know that rate constant K for a gaseous reaction is written as 2.303 divided by T log of P0 by P, where P0 is the initial pressure of the reactant and P is the pressure of reactant at time interval T. So now we have considered that the initial pressure of the reactant A as P1 and the pressure at a time interval T is considered as PA. So our formula will become K is equal to 2.303 divided by T log P1 divided by PA. Substituting into this particular equation, K is equal to 2.303 divided by T log initial pressure, that's P1, divided by partial pressure of the reactant A at time interval T is 2P1 minus Pt. So this is the expression for rate constant of a first order gaseous reaction.